Okay, so that leads us to an overview of the kind of machine learning, and which is really kind of a fancy, newly invented word for statistical learning, uh, which has been there for a while. So there are two main categories of statistical learning. They are called regression and classification. All right. So they differ in the goal. So regression means that given a certain, you want to train, in both cases you want to train an unknown model. So this model is something we don't know. In regression, the model has a task of taking a bunch of inputs. So let's say input 1, input 2, and you want to train a model to produce a desired output. In the case of regression, the output is continuous output. Okay, a continuous output means that, for example, you want to predict the temperature tomorrow, right? It's a continuous quantity. It can be 10.5 or 10.6, anything that's a real number. Okay, and essentially, for example, the classical linear regression you might have learned in any course in statistical method is basically having a y versus x relationship, and you're given a bunch of points, and you want to figure out a best line that fits these points, so that for any given x, so let's say you are asked to produce the output of this x, you're going to be looking for, okay, what is the y on that? So this is an example of a continuous output given some inputs. This is different from classification. Classification also wants to estimate an unknown model, and also based on a bunch of inputs. But the outcome of this model is not a continuous output. It's a bunch of discrete output. A discrete output means the output can be either this or that, right? A classical example in this case is a character recognition. So you get a bunch of images of 0, 1, 2, 3. So basically a set of images are handwritten, and you need to train a model to look at the image in pixels and figure out what number does this image represent. So the output can either be 0 or 1 or 2 or 3, etc. Right? It cannot be somewhere in between 1 and 2 or somewhere in between 2 and 3. So this is an example of a discrete output. All right. So today we're going to discuss how do we solve this kind of statistical learning problems with probably one of the most popular methods used today, that is to formulate the statistical learning problem, either regression or classification, into an optimization problem you can solve. And that links to a lot of numerical methods we have discussed so far, because if your model actually involves some model of a physical system, which can be then modeled using differential equations, ODEs or PDEs, then you can easily plug in this physical model and learn the parameters, right, of this physical model to basically serve as a physically informed machine learning. All right. So first, let's discuss how do we solve regression problems with optimization. So first of all, the first task is to decide what kind of model to use. So for any model, we are basically having a model that depends on two things. One is the inputs. So I'm going to write the inputs as X. And the two is the tunable parameters in this model. Let me write it as data. So this is supposed to give you an output that is that can be observed, right? And then you are given a set of known observed inputs. Y1 that corresponds to X1 corresponds to Y1, X2 corresponds to Y2, etc. up to Xn corresponding to Yn. So these are the inputs to this learning, to this training, right? So you are given this training data that you can use to train your model. So what does it mean by training the model? Training the model simply means figure out what theta, what are the tuning parameters in this model I should be using to get the best match between a possible future input and the future unknown observed output. Okay, so note that there is a subtle difference between saying that I want to produce the best match between the existing training set and produce the best match between a future data that's not included in this training set. Okay, so we're going to see that it's actually the latter that is important, not just the matching the existing data, which is often going to lead to what's called overtraining. Okay,